Hi there, Miss Barber here. This lesson is titled The Normal Distribution. The normal distribution arises so frequently that we give it special attention in statistics. Normal distributions always have the same characteristic bell shape and can be characterized by just two numbers, their mean and standard deviation. The mean determines the location of the bell's peak, while the standard deviation determines the bell's width. Here's an interesting historical note. Using data taken from French and Scottish soldiers, the Belgian social scientist Adolphe Quetelet realized in the 1830s that human characteristics such as height and chest circumference are normally distributed. This observation led him to coin the term the average man. Types of distributions. Data come in many different distributions. Some of the common ones are the uniform distribution. An example of a uniform distribution is the probability of a heads or tails of a toss of a fair coin. The graph looks like a rectangle. Another common distribution is the bimodal distribution. An example of a bimodal distribution is often the grade distribution of the first exam of a freshman math course. The graph indicates two clearly defined bumps or modes. Distributions may also be skewed right. Consider the graph of U.S. household income. Observe that it starts with high numbers on the left side and then skews to a shorter tail on the right side. Does it make sense to you that most household incomes are in the middle class range and that the numbers decrease as the incomes get higher? What do you conclude about the jump in the number of incomes at the highest earnings? Distributions may also be skewed left. Consider this histogram of the age of death of natural causes. Along the bottom of the horizontal, it should have ages on there. Even so, does it make sense to you that the number of deaths from natural causes increases as people get older? Finally, we're at the normal distribution. Consider the relative frequency distribution table of download times experienced by the number of subscribers for a math learning website that's provided below. The frequency distribution table has three columns. The leftmost one is titled Download Time in seconds. We read the download times as 0 seconds up to 5 seconds, but not including the 5. Go one column over, we see that there are 4 subscribers who experience that download time. The relative frequency is 0.4. Let's go down a few more rows and look at 25 to 30. That means 25 seconds up to 30 seconds, but not including 30. The number of subscribers who experience this download time is 194. Its relative frequency would be 19.4. That relative frequency distribution table is also presented for you as a histogram. Notice that the shape of this histogram is bell-shaped. Relative frequency histograms that are symmetric in bell shape are normal distributions. This shape is called a normal curve. Let's summarize the properties of a normal distribution. 1. The graph of a normal distribution is called a normal curve. The normal curve is bell-shaped and symmetric about the mean. Finally, in a normal distribution, the mean, median, and mode all have the same value and all occur at the center of distribution. Graphs of different normal distributions. Recall that the standard deviation is a number or statistic that measures the spread of data about the mean. A normal distribution has a bell shape. The spread and height depend on the mean and standard deviation. Consider the three graphs on the left-hand side. They all have the same mean, but have varying standard deviations. The height in the middle, that normal curve has a standard deviation of 10. However, when you consider the flatter, more spread out normal distribution, that standard deviation is 20. And the one that's very tall and clustered around the center, that standard deviation is just 5. Now, consider the graphs to the right. They have differing means, but have the same standard deviation. Notice that the shape is exactly the same. The height is exactly the same for all three of them. The only thing that's different is where they're shifted. The middle one has a mu of -1. That's the mean of -1. To its right, same shape, same height, but shifted to the right, the mean is 1. And then the leftmost one, same shape, same height, but the mean for this one is -2. Discovery activity will continue with, for the frequency distribution of the download times for a popular math learning website, the mean time is 30 seconds and the standard deviation is about 10 seconds. Let's write that out. Mu is 30, sigma is 10. Looking at this histogram, note that at the mean we have 30, and then we expand or we get smaller by units of 5 seconds. We're going to replace those actual download times with standard scores, letting mean of 30 be 0. Then, one standard deviation to the right, we write 1. 2 standard deviations to the right would be 2. 3 standard deviations to the right is 3. And then going in the left direction, the numbers would be -1, -2, and -3, respectively. Now, let's consider one standard deviation on both sides of the mean 0. We're going to add up the relative frequencies. For one standard deviation to the left, we would add 15.1 and 19.4. To the right, we would add 19.0, 14.8. The sum of the relative frequencies is 68.3. That's the percentage of the area under the normal curve between the standard deviations of -1 and +1. Let's repeat this process for 2 standard deviations on both sides of the mean 0. For one standard deviation, we've already computed that as 68.3. So let's extend another standard deviation to the left of -1 and to the right of +1. The corresponding relative frequencies are 9.2 plus 4.1, and then 9.1, 4.6. Add those together and you get 95.3%. That corresponds to about 95% of the area under the normal curve between standard deviations of -2 and +2. We'll repeat this again for 3 standard deviations on both sides of the mean 0. At 2 standard deviations, the total area was 95.3, and we will add the remaining relative frequency values. So we'll add 1.8, 0.4, 1.6, and 0.9. The sum gives us 100%. That's the entire set of data. What we just completed takes us to something called the empirical rule, which is also called the 68, 95, 99.7 rule. For normally distributed data, approximately 68% of all data lie within one standard deviation of the mean in both directions. Approximately 95% of all data lie within 2 standard deviations of the mean in both directions. And finally, approximately, pay very close attention to this, 99.7% of all data lie within 3 standard deviations of the mean in both directions. Let's depict that on a normal distribution. Between 1 standard deviation of the mean, that's between -1 and 1, you got about 68% of the total area under the bell curve. Between 2 standard deviations, that's between -2 and 2 about the mean, which also includes the 68%, you've got 95% of the total data. And finally, between -3 and 3, that's 3 standard deviations about the mean, you will have approximately 99.7% of all data. We say that standard deviations to the left of the mean are below the mean, and to the right we say that the standard deviations above the mean. Let's observe that this is symmetric. So if you wanted the area between 0 and 1, that would be half of the 68%, or 34%. Let's suppose you want the area between 0 and 2. Now you want half of the total area encompassed between 2 and -2 standard deviations. That's half of 95%, or 47.5%. Example: a student is enrolled in a class that is graded according to a normal curve. The student earned a 92 on the first exam and an 84 on the second exam. On the first exam, the mean was 94 and the standard deviation was 2. For the second exam, the mean was 78 and the standard deviation was 3. On which exam did the student earn a better grade relative to the class mean? The grade of 92 is 1 standard deviation below the mean, whereas the grade of 84 is 2 standard deviations above the mean. The student earned a better grade on the second exam. Example: the fuel efficiency of vehicles currently registered in a Midwestern state is normally distributed with a mean of 24 miles per gallon with a standard deviation of 6 miles per gallon. Part A. Find the fuel efficiency that is 2 standard deviations above the mean. So to compute this fuel efficiency, find the mean and add 2 standard deviations. Let's put the numbers into this formula. The fuel efficiency would be 24 plus 2 times 6, which is the standard deviation. The arithmetic takes us to 24 plus 12, or 36 miles per gallon. Part B. What percentage of vehicles get between 18 miles per gallon and 30 miles per gallon? To solve problems like this, always start with a sketch of the normal graph. Mark the mean as 0, and then appropriately mark 1 standard deviation, 2 standard deviations, and 3 standard deviations on both sides of the mean. Where we have 0 for the mean, let's put the numerical value given to us in the problem, which is 24. And then let's find the actual values that correspond to 1 standard deviation above the mean, would be 24 plus 6, or 30. We'll continue to go to 2 standard deviations above, so add another standard deviation to the 30, which would be 36, and repeating in like manner, 3 standard deviations above would be 42. Now let's go below the mean. So 1 standard deviation below the mean of 24 is 24 minus 6, or 18. Continuing to the left, 18 minus 6 is 12. And finally, at minus 3 standard deviations, the miles per gallon is just 6 miles per gallon. Mean minus 1 standard deviation would be 24, that's the mean, minus 6, that's 18. And let's go to above the mean. So mean plus 1 standard deviation would be 24 plus 6, which is 30. Let's shade the region between one standard deviation of the mean. That takes us between 18 to 30. By the 68, 95, 99.7 rule, we conclude that about 68% of vehicles get between 18 miles per gallon and 30 miles per gallon.